let's go back to business. Think about your question, okay? Please. Yeah, they were complaining that I'm not asking questions. Well, not always. I try to do it, okay? But, I mean, I came here to give a lecture. I'm not came here to listen, so, okay? That's not my job to ask questions, okay? This is your job. Okay, so let me finish with this exponential interaction. Okay, so next week we can discuss about 543. So we were discussing this model, okay, on R2. Yeah, I plan 15 minutes. Let's see how it goes. So we constructed, or at least I motivated to you how you can construct this object as the limit as regularization goes to 0 of essentially the exponential of beta phi epsilon minus 1/2 the expectation of beta square, the expectation of phi square, okay? As a random field, okay? This depends on a point in space. We did, and somehow I showed to you via computation of a variance that this object is in L2 for beta square less than 4 pi. Okay, this computation of variance was okay, and we renormalized, and then somehow, well, I didn't prove that the limit exists, but somehow with the computation of the variance motivated that we should believe that this is true. But actually, this object exists for all beta square less than 8 pi, but is not in L2, okay? Not in L2, as a random variable, I mean, okay? So this is L2 of the probability space. In space, unfortunately, you will have similar property. So this is called also the Gaussian, either the renormalized exponential of the Gaussian free field, but modern name is the Gaussian multiplicative chaos, okay? So it's an important object in modern, let's say, two-dimensional probability. It's related to the Gaussian free field. And it's so like in this context is seen, we try to see it as a distribution. You see, so far we just looked at random distribution, but this is would be a particular random distribution because it's positive. And now you have to remember that any positive distribution, it's a measure, okay? You can actually have a very good estimate of its regularity. So in L1, it belongs to B011, okay? It's a measure. So it's a measure. So actually, it will have a name. So you call it like it's a measure, it's a random measure to which every sect assign essentially formally you have to think of it as something like this, okay? As the integral of this distribution over this set, if you want. And then what we know about this random measure, so being a measure, you can integrate deterministic functions. So you can define object like this. And it's in L1 always, up to 8 pi. And essentially, it has a mean, which is given by the Lebesgue measure. Okay, so this is the mean of... so it's uniform. It's in average, it looks like Lebesgue, but actually it's a fractal measure, and we have seen some images in the talk of Felipe. Felipe, yes. And what we want to do is, so I showed to you that we can construct this model. So we take a function xi from R2, let's say positive, and compact support. And we construct a model by just using this as a tilt of the Gaussian free field. Okay, so this is the GFF, and we tilt it with the exponential of the Gaussian. So this is a random variable on this space. So you have to think of it as depending on phi. Sorry, I should write. Okay, so this is a function of phi, measurable function. You cannot recognize the exponential anymore, okay, because you multiplied with 0. Okay, you are the renormalization. You should think of this object as 0 times the exponential of the Gaussian free field. Okay, because this constant is going to 0. Okay. So you cannot. This is a very intuitive, just to remember where you come from. But this object has no algebraic property with respect to the Gaussian free field. Okay. It will have, but you have to prove. So every time you have to prove something, essentially you go back here, you do your computation, and then you go back. We will have to do this when we do the shift, of course. Okay. At this point, we just define this object, and it depends on all the parameters, but I just write zeta because I want to prove. So I want to ask myself what happens when this function converges to 1. Okay, this is the infinite volume limit. Okay, you take a function, then you make it converge in the suitable way to 1, and think about this function doing something like this. Okay, I don't want to be too precise, but because we don't do all the proof with all the detail, but essentially think about the function psi, a function like this, which is 1 in a bounded set and 0 outside, and then you send it to infinity. Okay, so this is a volume. You could imagine a function. So we ask, can we prove the convergence of this measure? And then we want to use this variational approach. Now we know everything. You need just to understand. So now we have this potential. I can call it the oxi of the Gaussian free field. Is just this function. Okay, and this is integrated over all space. And of course, this function. So this functional. Let me forget about beta. Beta is fixed in our thing. Okay. So now, if you want to use the variational approach, you need to write down the variational functional. So remember, so we want to write down f of z, and this was the expectation. And now we have, remember, okay, it was v oxi computed in w1 plus z1, and then there is the quadratic form of z. Okay, so this is our general strategy. And then the minimizer represents the measure. Okay, so remember, let's call zxi the minimizer. Again, I assume it exists, but you can relax the problem and show it exists. This is bounded below. This is also bounded below. So you will have a minimizer if you compactify your setting. You call the minimizer this, and the minimizer will satisfy. So the minimizer will have the following property, that the law of W1 plus the minimizer is exactly nu z. Okay, this is the relation with my problem in this setting. So we have to compute this object. Okay, so this is why I was insisting when you are in difficulty, you go back here and then you take the limit. In the notes is actually is done with a limit procedure, so you define the regularized potential, and then you take the limit. Let me just guess what is the answer. So I need to compute this in order to put it inside here, and in order to write the Euler-Lagrange equation for the minimizer. And what will happen? Okay, this was essentially, if you are before the limit, okay, you have the exponential of w plus z. So this factorizes. You will have the exponential of w with its own good renormalization, and the exponential of z. So the exponential of w, essentially this will look like the exponential of beta z1 times the regularization, the exponential of w, with the right renormalization, because w1 is the Gaussian free field. So this is a number, okay, but it's the right number for w1. So you have something like this, and then you integrate. So this object, you can imagine, okay, if you now take the limit, you remove epsilon, this object will converge to the Gaussian multiplicative chaos associated essentially to W1. Okay, just imagine it's, so maybe let's, I write it in this way to say, either you write in this way or, but in the notes I think it's written in this way. So now it's the Gaussian multiplicative chaos seen as a measurable function of W1, okay? You construct this measurable function of the Gaussian free field, so on anything which is absolutely continuous to the Gaussian free field, this measurable function makes sense, okay? It can be transported because it depends only on the law, okay? So essentially, as a measurable function of this argument is the same, but because you can define it there. And this is this measure. Okay, so my potential looks like this. Okay, so you see it's, and this is a measure, this is a bit delicate now, okay? This is create a bit of a problem in the paper. So let's say this potential looks like this. Please ask question if you find that this expression does not, so I will start to don't put it anymore because this is just a random variable. Like I know the law of W1, I know the law of this object, okay? So you have to think that my randomness now is W and this object. They are jointly defined, okay? I'm not looking anymore inside what is exactly, okay? Like before, think about in 542, for example, we had this family of objects. So somehow you have always to enhance your noise and you're looking at this family of random variables, which are the randomness which appear in my potential. And we don't use really very detailed information on how they depend each other now. So let's see a moment this expression. Do we agree that this procedure, so what I did is you go back here, you compute the shift, so you put here W plus Z. Now the exponential factorizes. And then what you have W with the regularization, you take the limit and see this will work, this limit will work as soon as phi has the law of the Gaussian free field. So you put W1 and you can do the same computation and prove that you have a limit which is the Gaussian multiplicative chaos associated to W1. But we forget about this. It's just a random variable in my probability space. Again, think about 543, we had these new objects which we created and this is no different. Just technically is a bit more involved. This is a distribute, actually not even more, okay? Think about in 5.4, you add a term like this, like Z, W, like you add a term like this. So you had to define this object, okay, I skipped this thing, but we said we know the regularity of this object, I know the regularity of this object, and essentially my bounds implied that this object is well defined as a multilinear form. I have good control. So here we have to ask the same question, but you see this is a measure, but Z1, if you remember, the only thing we know about Z1 essentially from the variational problem is that is in H1, okay? So Z1, essentially what we know is that is in H1 of the space variable. You can assume you can assume this is finite. We are in finite volume. Sorry, I forgot the volume will appear here. So this is like this, okay? This is a measure, so it's a measure. In average, somehow this is well defined because this measure, it's Lebesgue in average, so this function is integrable. Well, this is this is a bit of a problem, create a bit of technical difficulty, but Z with only this regularity, which is coming from this form, which is essentially this, that the endpoint is in H1, you don't have that Z is continuous. In two dimension, the embedding fails, okay? H1 does not embed in continuous function. H1 embeds in LP for every P in dimension 2, but not in continuous functions, okay? So this function is a lot of integrability, but not continuous. So this is a bit of difficulty here, but it can be dealt with. Let's say I just forget about this. Let's treat it as a continuous function. Okay, this composition is well defined, and you can treat this variational problem. let's compute the Euler-Lagrange equation, because, so now the goal is I want just to redo what we did in 542, so it's not very interesting. The a priori estimates are even easier. Here, it's really easy, okay? This potential is bounded from below. You can essentially ignore, and you can just use this, okay? So we have very, very easy a priori estimate. So let's write the Euler-Lagrange equation to see how we take the limit. So now the logic is the same, okay? The variational problem, I cannot take to the limit because this potential become infinite, and this form become infinite. So I want to write the Euler-Lagrange equation and then localize with a weight, okay? That's the goal, okay? The variational problem does not have a limit in infinite volume, but the Euler-Lagrange equation give me information about the sequence of minimizer uniformly in the volume. So how does it look like? Remember, it was something like this. It was 0 equal, let's do rapidly, the functional derivative of the potential in some direction, which I call K1, plus the bilinear form coming from the quadratic form, okay? And then if I compute this, I have to vary this parameter. So when I vary, I just get the integral. So let's so I have the cutoff function, then I have the exponential. I don't move the exponential, and then of course the exponential. I differentiated this exponential in the direction k1. So essentially, this gradient looks like this: beta k1 of x, and then everything multiplied with the Gaussian multiplicative Gauss. Okay, something like this. And then there is the quadratic form. I write it is like before, so I don't touch it. Okay, so I have a similar expression. Now, let me write something so we see some. In the notes, I do differently. I use the variational problem, but I want to make an observation using this equation. Okay, the Euler-Lagrange equation, it has, remember, it has this weak form, but it has also a strong form. Okay, what is the strong form? It looks like this: 1 minus Laplacian z dot s. Okay, so you essentially find. You choose accurately this K1, and you prove that essentially this expression has to be true for every this expression has to be true. So what I will have here, I will have something like exponential beta, exponential z1, and then this measure, okay, dm. Let's write it as a density, of course, but this is meaning this the distribution associated to this measure, okay? I just want to deal with the distribution. It's fine, okay? I want to write it like this. What you note about this, okay? This is a positive distribution. Okay, what you note about this formula. Okay, so the right-hand side. So remember, in 543 case, this would be a polynomial without sign, but you see in this case, this is positive. This is a positive distribution. This is a positive object, and it's negative. Okay, so this object is less than 0. So this quantity is less than 0. Okay, so it means that z is negative because it has derivative. Well, this is a positive operator. So think about bringing on the other side would be an integral with an integral operator with a positive kernel. So this means the derivative of z dot is positive. Essentially, this implies that derivative of z dot is negative. And since it starts from 0 and is negative everywhere, this implies that z is negative everywhere. Okay, z in times. Okay, so in this problem, so this is very nice feature of this problem. In this problem, the additional drift you have in the minimizer, it's negative. Okay, another way to prove it, this is the way we use in the note, which is more fun. is to prove that if in the variational problem I replace z with minus its absolute value, I get a lower value, always, okay? Because these get lower because you replace the exponential with minus a positive quantity, so it goes down. And the quadratic form, this is an exercise for you. The quadratic form, H1 norm, it's invariant under this thing, okay, by the chain rule, because H1 support taking composition with absolute value, okay, so this will not change. So yeah, the way I choose in the paper, say, if you have a minimizer, then minus absolute value is still a minimizer, so any minimizer is negative, but you see it clearly from here, from the variational problem, okay? So this is a beautiful feature of this problem. It's very impressive, actually. It tells you that the interacting field, so this is the exponential field, if you want. It's the Gaussian free field plus something which is negative. Okay, so the interacting field is always below the Gaussian free field, even if the Gaussian free field is a distribution, in the sense that the difference of these two distributions, you have a coupling in which the difference of these two distributions is positive. Okay, so it's a measure. Okay, it's very, I find very beautiful property. Okay, because you see, this is the only problem where I see this thing happening. Okay, so. And so you see, since if you take a cutoff which is positive and which is increasing, you are gradually pushing down more and more. Actually, okay, there is some monotony in this problem. You are pushing down more and more the Gaussian field. Okay, so the limit is not difficult to take limit. So essentially, by these properties, you have. Yeah, okay, let me observe. So this is the first observation. Then there is a cooler observation that because z is negative, this object is less than 1. Okay? So the potential of W1 plus Z1 is always less, it's positive, and is less just the total mass of the Gaussian free field. Okay, because Z dot. Okay, so you have upper and lower bound on this quantity, okay, which are uniform in Z1. Okay, and in this case, essentially, you can even say that 1 minus Laplacian Z1s is smaller than is bigger. Okay. Wait. Now I get confused with the minus sign. Okay, so I make this bigger. I take beta positive because anyway it's not very important. You can take beta positive. If I put 0 here, I will get a larger quantity. So this is bigger than minus the conditional expectation of beta dm over dx, okay, which is a positive quantity. Yeah, so you have an upper bound for z and a lower bound for z. Yeah. Sorry, I forgot the cutoff. Okay. Sorry?
The upper bound is only with respect to W1, right? The integration measure?
No, in the upper bound because, so this maybe I got it wrong. Let's do it again. This potential is like that, and z is negative. So this is less than 1. Is bounded, okay? I'm not sure. So the W1 is inside. Yeah. There is the measure. The measure is the exponential of W1. Okay. So this is still random. Okay. Yeah. And if you take the average is between the two. Okay. But somehow you have upper and lower bound, and you have an upper bound for the pathways for the solution because it's bigger than this number. So this does not depend on z anymore. So you have upper lower bound on z. Okay, z is a bounded function between these two quantities. Okay. This is a distribution, but when you integrate with the its kernel, it will be in L infinity. So actually, you check that it's a random function. Okay? And this gives you tightness, and you can take limits. Okay, so I don't. Otherwise, I spend another hour to do this. I want to do 5 for 3. Let's say this is a very nice situation. If it's a bit tricky to deal with this object because it has not a lot of integrability. So you see, when we use base of spaces to compute the regularity, in the polynomial case, we use the fact that you can live in every LP and you can take average of the LP norm. Here you cannot do. So actually, this object lives only in base of spaces of regularity, of integrability, very small integrability. Yeah?
Is it true that this minimizer z of xi is a monotone function of xi?
If xi is positive, yeah, it's monotone because you are increasing.
So then in your limit, the uniqueness would be easy just with that?
Yeah, but I want also to show that there is a unique minimizer. Okay, so I can formulate the problem in infinite volume, and they did identify the measure in infinite volume uniquely. So, this is a very easy problem. There is a lot of monotony. Actually, it's easy, but it's a very interesting problem. Okay, in the sense that this model is related to the Liouville model, and there are a lot of progress. It's a conformal quantum field theory if you remove the mass. I don't want to enter into this, but it's a very profound model. It has a very nice properties, okay? Because somehow you are perturbing the Gaussian free field with something which is intrinsic to the Gaussian free field. So this gives a lot of nice property, which phi4 does not have. But let's not enter this. For us, it's a toy model. Gives this exponential has this very nice property. The only problem is that it lives only in some kind of space with very limited integrability. So p is less than 2, okay, depending on beta actually. So this creates a bit of technical problem when you want to do your estimate, because you see we enjoyed a lot the fact that we can put like this object can be put in B infinity spaces. Remember, okay, this object would live here, and this we use a lot. And here, this object only belongs to some limited regularity with p less than 2. Okay, so you have to play a bit with that. P is bigger than 1, that's good, okay, but less than 2. It's big, and with some negative exponent. I don't want to enter this right now. You see, it's a measure, but when you want to prove something about it and you don't have a sign, then you have to use that it's a distribution and it's of negative regularity, but it's of limited negative regularity. Anyway, so now from this, you get that this family is tight. Let's misk it. And it has a limit, and the limit you can imagine satisfy this Euler-Lagrange equation. So this I want to show you a case where I can prove uniqueness. This is the only case, so I think we should, that I know of, where I can do this. So I think we should appreciate it for, at least I can do it in one case, okay? So the theory is not empty. So the limit infinite volume Euler-Lagrange equation looks like this, is something like this. I want to write in the weak formulation, so it's the expectation. It's the same thing, okay? But the potential now is in infinite volume, W1 plus Z1 and K1. And to make sense, you take this compact support, because otherwise this integral is unbounded. And also the quadratic form will be unbounded, because in that case, Z will be different from 0 everywhere. But Z is a nice function, okay? Z essentially lives in L infinity of the full space, okay? It's bounded. It's bounded because you have these two bounds. Actually, I'm not sure if, no, I think it's okay, yeah. You should. Okay, so how does it look like, this quadratic form? I do the computation. This is now the integral over the full space. You have beta zeta, and then you have beta k, and then you have d mu. And then you have the quadratic form. Let me write the quadratic form just to be clear. Is the integral on 0, 1, the integral over R2, and then you have essentially yeah, ks dot multiply 1 minus Laplacian zs dot, okay? Something like this. Now, to do a priori estimate, so now I want to, so what we want to do is uniqueness, okay? So I want to prove that there is only one function z which satisfies, so we have uniqueness, okay, by convexity. This is common theme with just 10 notes, okay? Convexity give you this positive curvature, but also and this positive curvature give you a way for trajectory to go together. So the idea is that, you see, k is a variational parameter. So this holds for every k, and I want to tell you that there is only one z which I know existence because I constructed by compactness.
Z equals 0 satisfies that equation.
No, it does not satisfy this equation. No. Z0, this is 1. No, it does not satisfy the equation. You have a source term, which is the measure. No, z is pushed down by itself, you see. Well, it's pushed down, and if z become very negative, then the push down disappear, okay? Yeah. Is it okay? Yeah. Yeah, I was fearing that. No, but because the potential is there, so you see, the potential is an exponential. So you see, you want to remember, you want to minimize potentials, okay? So essentially here, you want to have z very negative. That's why z is negative, okay? You don't have any incentive for z to be positive because it will just increase the exponential. Or you want z0 give you some, this will act, and you want to turn it off, so you send zeta to minus infinity. That's why you have a negative drift. But of course, if you push it down too much, you pay in the quadratic form. So you have yeah, this is the balance, okay? The balance satisfy, the equilibrium situation satisfy this for every k, okay? You are a first order condition. There is a second order condition, of course, in the notes is written down, which you are in the minimum, so the second order say you are a quadratic form is positive, but I don't know how to use it, okay? If you find an idea how to use it, it would be, because give you some information, but I don't know how to use this information. Okay, so how we do this? We do like path coupling. So we look at two solutions and we take the difference like we did yesterday. Okay, this was the reason for me to spend some time in that easy computation so that we do it again today. Okay, so you find, you look at two solutions, you call it Z and Z tilde, let's say. You imagine that there are two solutions and you want to prove it's unique. And there is not much fantasy, okay? It's you have to do this computation, okay? You look at the difference, I call it delta, and then you try to prove something for the difference. So how it works here, yeah, you have two solutions of this equation. So since the two solutions satisfy this, you can sum, I guess. Let me see. No, maybe I want to take the difference. Yeah, I want to take the difference so that here appears the delta, and here appears some combination, and then I want to use k to have convexity. Okay, so essentially you take delta like this, you take to be the difference of the two. You can, I guess, put a weight if you want, because the solutions are different from zero everywhere, so you have to pay attention to that. So you have to put a weight, okay, to make sure that this k. So essentially, you want a weight which is compactly supported so that you can test with that, and then you take the limit with a weight which goes to zero because you want to keep this quadratic form finite. But essentially, you multiply with that, and you obtain something which is like this. It's zero. I think this is now follow the pattern exactly of the proof of yesterday, okay? Because we use convexity for the 4 power, and here we are using convexity of this potential, okay? The k point of this model is renormalization is multiplicative, so it didn't affect the convexity. And now it's not clear what does it mean. You see, this is not really an exponential, so you don't know what does it mean convexity. But the point is that in the variation, in this formulation is very clear. In this parameter is an exponential, so it's convex. Okay, so let's use it. I take the difference of the two solutions. So you have the integral of, you have rho, you have beta, and then you have exponential of beta z1 minus exponential of beta z tilde 1. And then you have z minus z tilde, because this is kappa. And then you have dm, which is just a spectator. This is just the measure. You see, in this problem, the natural measure is given by the Gaussian free field. It's not Lebesgue, but you integrate. And then you have the quadratic form, which is the integral over R2. Okay, integral over ds. And then, okay, let me write it like this. I think it's easier to see what's going on. It's scalar product in R2, in L2 of R2 of delta, yeah, okay, z minus z tilde dot s 1 minus Laplacian z minus z tilde dot s. Okay, and this is in L2 of R2. And all this is inside the expectation. Okay, so we took the difference of the two equations and we used this variation of a classical thing. Okay, and now because z is convex, this is positive. Okay, so by convexity, this is positive. Of the exponential function, you see, this is the increment of the exponential function with the increment, and you have to compute it. I mean, I'm saying it because I know the result. Okay, it's not that I see this expression, because I always get confused if it's plus or minus. So you have to do a computation. Okay, but it's going in the right direction. No? You see, you're incrementing both things in one direction, and then it increases. Okay, this is an approximation. But I'm always scared that I get the wrong sign, so I have to do it. Or write, or yeah, you have to look at a graph. Okay? Anyway, it works, so this is positive. So you say, so 0 has to be bigger than this guy, which is positive, okay, because it's a norm. Okay, so 0 has to be bigger to the norm in, you see, this is essentially the H1t, maybe homogeneous H1t norm, and H1x norm squared. Okay, this is exactly the quadratic form. Okay, it was our quadratic form calculated in z minus z tilde. Okay, which is positive, so the only possibility is 0. Okay, so this gives you uniqueness. Okay, it's a trivial computation, but it's the only computation I can do. If you try this computation in 5.4, renormalize, you have the renormalized, well, what replaces this will be the renormalized square, essentially, and you don't know, is not convex, okay? Yeah.
Initially, you said that we assume that z is continuous, right? Here, to prove uniqueness among the...
No, well, somehow it's continuous. I think in the note, I don't remember exactly in the notes if I think from here you can prove that, yeah, it's continuous. Well, if you have to, no, the point is that any weak solution will be continuous because it satisfies an equation like this. So this is a positive measure, then you increase the regularity, this will be better, okay? It will be at C2 essentially. You see, so it's very nice function, it's bounded. Sorry, it's not C2, but it's good, okay? Because this has negative regularity, so you regularize by 2, you certainly get something which is in L infinity and continue. I'm not sure what is your question. So you no, the statement is any two weak solution of this thing. So the only thing you assume about these two objects is that they belong to H1 locally, well, H1t and this space, okay? Sorry, this is, of course, I had the weight. You have to do a bit more work because there is the weight around, okay? But essentially, up to correction, you prove the same thing because but this is on the weighted space, okay? This is technicality, so let's think about finite volume because in infinite volume, you have to deal with this and the weight, somehow this quadratic form can control also the correction term you create by putting the weight in the right way, okay? There is a computation to be done, but it's not very important, okay? The point is that this is the only case, I mean, uniqueness in infinite volume of this Euclidean quantum field theory from the perspective advocated in this lecture. It's a difficult open problem, so you are welcome to join the effort. And this is the only case where I can do. It's trivial, I know, but then as soon as there is no intermediate problem, because renormalization creates a lot of rigidity in this thing. You cannot choose an intermediate problem. Either you have this or you have phi4, where the potential. Okay, let me comment about this, because this is an open problem, something maybe somebody wants to think about. I don't have any answer. So what happened in phi4? Why I cannot do uniqueness? Uniqueness for phi42. I told you there is a recent paper on the archive by Bauer, Schmidt, Dugalier, Weber, where they use a sophisticated tool, in particular Log-Sobolev inequality, and for the Langevin dynamics, to prove that there is a unique measure in high temperature. Okay? Actually, they do it until the Log-Sobolev inequality holds, which is until the critical temperature of the model. But let's say high temperature, it's already good enough for me, which means small coupling constant. So you have a constant in front of the 4 power, it's small. Okay, you have something like this and lambda small. Okay, you should have uniqueness. But if you try this computation, you end up, you see, if you try this computation, you will have something which looks like W1 plus Z1 cube minus W1 plus Z1 tilde cube, and then multiplied by Z. So the only thing that changes is the potential, which will look like this, and there is the weight, sorry, the weight, I put it there. Okay, this looks like, okay, you say, well, how you see that? Well, this looks like morally looks like something like this. If you try to do a Taylor expansion, this is no much better and no much worse than something like this, okay? For example, okay? So, okay, try to expand, and then you have the square, and then you have the increment, okay? Just I did that very vague approximation. There is no claim. Anyway, I cannot do anything, okay? So, but what is the problem is that this is most of the time positive. So we understand how it works, the square, the renormalized square, okay? It's most of the time very positive, but few times very negative. And because you have this negativity in some point of the space, essentially what you should imagine happen. So this act, you see, this is like an elliptic equation for the difference, okay? So this act like a source term for an elliptic equation, where most of the time is killing the solution, but sometimes is increasing the solution, okay? So if you follow the solution along a ray, essentially decrease very much, but then you find a place, at least I cannot exclude that you find a place where this is very large, and then even if it has become very small and you want to argue that it's zero, so you want to say that whatever was the solution, it has to be zero at some point, and then let's think dynamically because it's easier. But then at some point, any small difference could be amplified. So even if these two objects are far in the future very different, there is no stability, you see. No? You get amplified, then you go down, then get amplified. And now the question is the insurance going broke or not? Okay, this is like an insurance. No, you gain money, and then you lose money, and then you gain money, then you lose money because people break their car. And then you have, it's an actuarial problem, okay, but in space. So it is more complicated than just looking at the PDE as it is, okay? When it's convex, the potential is always positive, so you're always killing the particle, and it's going to zero, and then it has to be zero, okay? But here, we don't know, okay? So this is the problem in 542. So the model is simpler, is more natural, but it has this difficulty. Okay, so, yeah.
Do we know that when the Log-Sobolev inequality stops, you don't have uniqueness anymore?
For their case, for the Langevin, you see, here there is no dynamics, okay? So here I think people have to invent tool to handle the elliptic case. I think they proved because they have an implicit criterion. They proved that in the previous paper with Bodino, so Bauer, Schmidt, Bodino, and Dugalier, in another paper, they proved that log Sobolev holds until you have a certain estimate of the correlation on the interacting measure. And this should be the point where you, so this is the definition of one definition is where the two-point function is not integrable anymore. Okay, so this is very, very satisfying and physical way to detect the phase transition in this kind of model. This define, actually the divergence define one of the critical exponent. So they have an implicit criterion. So you don't know where is the phase transition, but this is exactly the definition, a good definition of the phase transition in this model. Yeah, you have to look, so sorry, I'm mentioning, so you have to look at somehow a spin at the origin and the spin at distance x. You take the average, okay, in the measure, in the 542 measure. So it's an implicit criterion. You take the measure, you look at this function, and for certain temperature it starts to be not integrable. So, but as long as it's integrable, they have a way to boost this into log Sobolev inequality. Their own version of log Sobolev is this multi-scale Bakri-Emery, but this is enough to prove uniqueness. Okay, other questions maybe? Okay. I don't want to call always Hugo because he will have he will start to hate me, but I don't remember any name. Apart Felipe, but Felipe, you have questions?
I don't know how much you know about the 542 correlation, but there is some form of like these topological phase transitions or not, like up to some temperature you have really long.
Yeah, well, somehow they're using a lot of property of 542. So in my mind, I would prefer to have a proof which is more robust, like PD-like. But of course, I mean, anything is good at this moment. So 542 is a ferromagnetic kind of system. So it has FKG inequalities. You prove them in discrete. You derive consequence for the limit. And this helps to boost this very weak information into log Sobolev. Okay, but it's a ferromagnetic system. So you have a lot of monotonicity going on there. Okay, this is an increasing, somehow increasing function. So you know if the temperature, I think, yeah, you know a lot of things about it. But I'm not an expert, so don't ask me. Don't ask me this question, okay? And this is a PD argument. And again, this equation, I mean, Justin was asking me, is this method better than, or better, or how does it compare with Langevin? In my mind, all these methods are drawbacks. What would be a competitor to this method? In this case, you study the Langevin equation for a long time, and you find stationary solution of the Langevin equation. You have the same problem. Uniqueness of stationary solution of the Langevin equation is exactly a problem similar to this. And you see the problem so what is the problem here? The equation is very well behaved, but since you start in the full space, you don't have a bound. You cannot start from one point where the two solutions are equal and then deduce they're equal everywhere, like you do for evolution, initial value problem. There is no boundary. You cannot do the boundary value problem starting from the boundary in. There is no initial value problem. So this problem is like an elliptic problem in the full space. You have two solutions, and a priori they could be so far apart that there is no way for you to understand the thing. Okay, and then maybe there is some topological method which exclude this pact. Maybe if you have two solutions, you have to link with an homotopy and then deduce consequence. I don't know. I mean, it's an interesting problem. Okay, so let me stop with that. In the next 2 hours, I will start to talk about 543. Okay, at least I think I have 40 minutes, so it's even a bit more, I think. But please ask questions. Now we are going in a more difficult problem, okay? So bear with me. I think I was aiming to have all the second week for that, but my plan didn't work out very well, apparently, which is good, because then you you will not be tortured longer than necessary. Um, we can do another model, but I decided not to include in the lecture notes because I discussed it in Cetraro, and there will be some lecture note, which is the model with the cosine. Okay, the cosine can also be handled in this. There is a paper with my student, Sarah Genmeyer, which do all the property you like about the cosine. Okay, the cosine is very nice. The cosine is nicer, and there you can have you can prove uniqueness for small interaction, for example. That is okay. Why? Because the cosine is bounded. When you renormalize, it become unbounded, but somehow some kind of unboundedness we can handle is Lipschitz. So if you put a small constant in front, you can use contraction method to prove uniqueness of the elliptic equation. Okay, it will have a Lipschitz vector field in some sense. So you can, for small lambda, you will have a unique solution. In that case, you see somehow the potential can be a bit negative, but somehow the constant term always beat the potential. Okay, so you can prove the graph I put it here of amplification of small disturbance will not happen for small interaction. But you hope that this is true for every model. Okay. Okay, let's look at 543. This was our first application of this method, and somehow, if you want to be serious in this business, you should be able to do this model. Otherwise, it's not very. Nobody will even look at your papers, essentially. Okay. Well, it's not true, but somehow, for a long time, this model was only solvable with very hard constructive technology. Actually, it was solved first time when I was born in '74, more or less. And it's a test bed of technology. And yeah, I mean, all the paper is very complicated. So it's not that we simplified to a level which I would like. I think it should be simpler. So the proof we give has some unpleasant features, but at least I understand it. Okay. So, and this we'll do on the torus because it's already difficult enough, and I think is not done. Okay, on doing what I'm doing on the full space with the idea I showed you, tightness and things like that, it's an open problem. You're welcome to do interest about it. Okay, so we are in 3 dimensions, and we look at 5-4, and now remember. So now I have to do something. Because remember that the weak power does not exist, okay? So I cannot just look at the weak power like we did. We have to do more careful, and we have to do a scale by a scale decomposition. Let's call it scale decomposition of the Gaussian free field. Okay, so I need a different interpolation. Okay, we use this very mindless interpolation where we just increase the variance gradually of the Gaussian free field. I need this graduality to use calculus. Okay, this is what gives me this variational problem. So I need another way to do it. And so I construct now my Gaussian free field. First of all, T will be just any number up to infinity. Infinity is included. So this is a compact interval, okay? In this problem is not infinite, okay? Because I can arrive to infinity. So it's just a convenient parametrization of a compact interval, but it's a closed interval, okay, for me, in the natural topology of this problem. So I construct this. You see, before I was just, so I'm doing something like this. Before I was just putting the Gaussian free field, the covariance. So you see, before it was something like this. So I color a bit white noise. This is white noise with Brownian motion in time, but in space is white noise. You color a bit, but here you have to do more. So before was like this. Okay, so as soon as you arrive at 1, you have enough variance and you are done. Here you want to arrive to infinity, and you want to add white noise gradually at every scale. Okay, you add the right amount at every scale, and then you increase the scale. Okay, so you will get, you put here a smooth function which cut, somehow this function looks like this in Fourier space. Somehow this is the operator D, and at scale S it will add frequency around the scale S. Okay, remember this is a Fourier multiplier. So I'm looking in Fourier space and I'm adding frequencies around the scale S. And you want to do it in the right way to have a limit. So what's going on with this? The variance, so so WT, let's say WT, so you look at WT in 2 different points, you use Ito formula, and this is 1 minus Laplacian minus 1, and then you have the integral between 0t. Yeah, they commute with the Laplacian, so here you just have the square, the S, and now you want this object to be like some function rho t d. Some regularization of, and rho should be like that, okay? So essentially you start from rho and then you derive what should be the form of sigma, okay? You derive rho and you take square root and you get sigma. It's not very complicated, but rho look like this, okay? You have t, this is rho t of d, and this is d. Yeah. So essentially you include all the scale up to t, and rho t of d converges to 1 as t goes to infinity. Okay, so this is a regularization like we did of the Gaussian free field. Okay, so the law of Wt is exactly the law of the Gaussian free field multiplied with rho t d. I think 1/2, okay, if you want. Yeah, maybe I want. Maybe I want a square here so that I can put rho t d. Okay, so it's just a regularization of the Gaussian free field at time t. While before it was a multiplication, t times the Gaussian free field. Here we take the Gaussian free field and we cut all the frequency higher than I. So it's a smooth function, and this will be a smooth function, but then the law. This is all I want. The law of the endpoint is essentially the Gaussian free field. Okay. Or if you want, okay, here maybe something like this. Okay, I don't know. GFF is its law, and then you just multiply with it. Okay, so this is all I want to run my program. So this embedding is arbitrary. You do it as you like. I found these two to be helpful. In 2 dimension, there is not a lot of singularity, so you can just add all the frequency at once, and you increase a bit the variance, okay? And here you take variance 1 for the low frequency, and you add the frequency like that, okay? You turn on the frequency a bit. This function starts to do like this, and you turn on all the frequency. Yeah, it's Gaussian, Yeah, I'm taking, it's just this. It's just a martingale, a Brownian martingale. So the point is I need to have my Brownian motion. So these are the underlying Brownian motion to which apply the Boué-Dupuy formula. So they will be colored only, before they were only colored by this operator. So this is why in the quadratic form for Z I get this operator. Here it will be a bit more complicated. Okay, so I will not, in 2 dimension, I just look at Z. Here, I will have to look at 2 quantities. So let's write how does it look, the variation. So the Boué-Dupuy formula tells me that I have to look somehow some functional, which looks like this. So U is the control. Again, I go in the original Boué-Dupuy formula. U is the control for the Brownian motion. Okay, I control this Brownian motion, and I have to color it. So the entropy will be the L2 norm of U. Okay, so this is the easy part. So the entropy will be the norm of U squared in L2 0 infinity. And I do on the torus, so this is L2 of the torus. This is my adapted control. And then here I have to put the energy. So this is the integral on the torus. Let's call Kamal the torus, the cube, any torus. And then here you have to put, now I have to do the regularized problem, okay? Because here removing the regularization is the difficult part. Okay, so I look at the regularized problem. So the potential is just the 4th power renormalized. So now, okay, I have to, okay, I'm going too fast, okay, here. So I start to put just the 4 power. This is z. I will tell you what is the relation between u and z. Z is a function of u. So you put the 4 power, and then you have to put other things. You have to put numbers. So now you have to remember, before I had this weak product, which was that 4th order polynomial with second and constant term, with certain constant. Okay, now the constant will be different, but I still have the same structure. That is, I have this minus that minus another. I don't remember now what. Maybe I should copy. Yeah, I don't remember how I call the constant in the notes. One is gamma. So let me see. Yeah, let me use some constant because so gamma alpha 1 and alpha 2, and alpha 2 is constant. Okay, so and I subtract them. Yeah, so this is my potential. Okay. If I fix them as in the weak product, I will obtain like the expression in 2 dimensions. But here I need more renormalization. Okay, this is the difficulty of this problem, is that this object has to be renormalized in a more complicated way. There will be a first renormalization. So there will be, I can do a first renormalization, which is like the weak renormalization. So I can replace this with the weak products. But I have to remember, I still have to subtract something. So you can, I mean, these are, I'm also always talking about second order polynomials, okay? So you always have, sorry, I just want to write down what are the right constants. Yeah, here I have gamma. So I call it gamma of t of the second order guy. And then there is delta of t. Okay, so essentially this is what you write, and then you do a first renormalization, so rewrite things with weak powers. This fix some constants, and then you have residual constants. Okay, and exercise, find the relation between these constants. But we are just talking, this is a 4th order polynomial, this is second order, so you see that you can do that. And now the point is that even if you did weak ordering, you still have, so weak renormalization, like in 2 dimensions, this is not enough. You still have to subtract something, and it's convenient to write it in a weak form to do following computation. Okay, this is the novelty, and we have to understand who are these objects. Okay, this is the difficulty of this problem. Okay, now the goal is to find, to proceed like we did in 2 dimensions. Okay, so the first thing you have to understand about this variational problem, if this function is coercive. Okay, you want to say, can I fly to minus infinity or not? If I can fly, then there is no minimizer, and the variational problem is not well posed. No? So I want to show, and the logic is the same. Okay, here I will have the 4 power of z, and I have this object, which was the entropy before, and they have to control all the other terms. So let's see if it works. The first observation I want to make is that now you look at this object of, I use it as if, so sorry. So what is zt now? Zt is what remains if I shift the Brownian motion with u. Okay, essentially B got shifted, remember what happens in Bouet-Dupuy, B got shifted by u, essentially Bt got shifted by the integral of us ds. Okay, this is like Girsanov formula. And then Wt means that got shifted. This B get a shift, so this will become us ds, and then you get this shift. Okay, so you get shifted with Zt, and Zt is exactly the integral of 1 minus Laplacian minus 1/2, and then there is sigma of d, this multiplier, and then you have us ds. Okay, so u is an L2 function, and then you take only a small part of this L2 function and you create z. Okay, so there is a lot of redundancy in this problem, but we don't care. Okay, in particular, you have always the same estimate that supremum for all t, t bigger than 0 of zt in H1 is controlled by the L2 norm, the norm of U in L2. Okay, so this computation is in the notes, but essentially this is L2 spacetime. Okay. But this is exactly what we had before, okay, just written in a slightly more involved way. Okay, so we have essentially, we know that Z is in H1 and is in L4, Z1, okay, Z1 sorry, now is Z infinity, in L4. Or actually, yeah, actually it's not even Z infinity, because if I regularize in this way, it's ZT. So I know that ZT is in H1 and ZT is in L4, okay? This is all the estimate I have. And I look at these objects. Now you start to write down them. So remember the bad guys. Now this is the second film of the series. The first film we won, but in the second it's harder, of course, okay? Otherwise people don't get, it's like John Wick films. So you get harder and harder. So we have to work harder today, okay? So the badder guys, okay? So who are the badder guys? Let's look at them. I expand. This will be there to cure things. So this will be the ugly guy who helped us this time. But the bad guys are inside there. And one of them is, this is okay. Okay, this is making a lot of noise, but I don't care because I take the average and make 0. Okay? Because there is no Z. Okay, this is good. Yeah. Then I look at the next one. The next one looks like this. Okay? This is the space integral. Okay? This is really ugly. Okay? This is very, very bad. Okay? Well, I cannot, this is Keanu Reeves, but you cannot see it. Why it's very bad? Okay? Because this object does not even exist in the limit. Okay? So W3, T does not, well, WT infinity does not exist. So I cannot even start to try to prove something uniformly, because even this is infinity, this will not, and bounded, this will not be enough to make this object uniform in T, okay? What does not mean is that I don't, I mean, remember, I cannot prove it that does not exist as an object, but certainly I cannot be able to do any estimate. So you take WT, remember our method need to take average, so you can take any power, even the square, and you take a very negative, like Sobolev norm, whatever, you can put whatever number you want here, but this still go to log, this goes like log T. Okay, this is meaning, okay, it will not, decreasing our slackness will not suffice to make it well behaved. Okay, so this is not, we don't have uniform estimate of this object, of this kind of norm in average. Okay, let's say I take the average and I take norm here. You don't have any way to estimate this, so our method will not work. Okay, we have to get rid of this term in other ways. Okay, so this is the main problem. There is another problem, which is the other term. So the two bad guys in this business are these two. Okay, why I'm claiming that? Well, this is W3. Sorry, this is W3. So let's go back and refresh the regularity of this term, because we will need it. This is what changed in 3 dimension. Okay, in 3 dimension, we have the W, essentially W. So what I mean regularity, these objects are smooth. Okay, the point is that I want to estimate uniform in T to be able to take the limit. So what I mean is that, well, this object converges to W infinity, and W infinity in C1/2 minus kappa. Okay, I'm on the torus, so there are no weights. And then W2 infinity is still good, but is belong only to C1 minus kappa. Okay, so this is substantially worse than what we had, okay? In particular, you see that this is really problematic for us, okay? Because the only thing we know about Z is H1 at best, and not even a lot of integrability, and this is less than C1. So this guy cannot be multiplied by Z, and I will have it here. So this, okay, so we cannot multiply it by Z. Okay, because Z is only in H1, so not enough regular. Okay, this is the only control we have. To dimension what was a toy model with respect to that. Okay, we lost a full degree of regularity, and this is what all we got. So this term is very bad shape. Okay, so this term, it's really worrying for me. Okay, it's inside here. Then there is another term. This term is good. Okay, there will be W times Z cube, but this is okay because W is in C1 half. Okay, this is okay. So far. Okay. Well, when we go on, this is like John Wick movie. So when you go on, you get blessed. So you're not able to do things that you were able to do before. So it looks in good shape, but we are going to change to solve this problem. We are going to introduce another problem, and now this will require some help, some manipulation. Okay. So far, at the beginning of the movie, this looks fine, but later on, not. So let's. So, but for the moment, you are really worried by this. Okay, this is like the first level. Actually, in my mind now, I also have the film of Bruce Lee. No? When he, okay, this is maybe Bruce Lee when he goes into the level in the house, and so this is the first bad guy. Okay, the blonde, whatever. So how we do with this? So this is this we need a new trick. Okay, the trick we have, because the trick we have was also only estimating and say that it's good. I have to remove this, so something has to happen. And somehow, if I don't remove it, what could happen is that this object goes to minus infinity, because the fact that I cannot control it means that it can be very negative. Okay. So there should be something which pushes it up. So I need to push it up, and the only thing that I can use, I cancel is the U square. Okay, it's the only term I know how to use. So let's see. So essentially, we look at this term. So there will be this is a time t, and then you have 1 alpha, and then you have this L2 norm. So this looks like this. Okay, US squared ds. A priori now is up to infinity, okay? You control all the process up to infinity. So now I look at them. Of course, I'm simplifying. I'm ignoring the other, but let's imagine the other. I treat it later. So what I want to do, this is somehow good with respect to that because it's linear. So what I want to do is the only thing you know how to do in life is complete the square and use Cauchy-Schwarz, no, whatever. But complete the square, this could be a good thing, because this is a polynomial thing. So let's try to complete the square, but I have to find, so Z is the integral of U. So somehow what you want to do here is that on this term, you want to develop along the scale parameter, because this is only at the end time. So you can compare similar objects. So you write this object as the value in 0. No, you use Ito formula, okay? This is why I wanted the martingale. This is a bounded variation process. Is derivative is in L2 of the parameter. So is order continuous. So is bounded variation. You use Ito formula essentially, but it's not even Ito formula because there is no correction term. Okay, this is a martingale. This is a bounded variation process. So there is no cross term. You just have so you have a term which looks like this, is W3S. So now I'm using that this fact is a martingale, okay? And then you have Z dot S ds from 0 to t, and then integrated in space. And there is a term when I differentiate this, but it's a martingale, so I ignore it, because at the end of the day, I take an average. So the martingale will not change value, okay, for whatever control you have. So you have this, plus now I have this. So what is, Now let me use a notation for this. So whatever is multiplied u, I call it j. J is, so it's the Laplacian and the sigma. It's an operator I don't want. It's a self-adjoint operator I don't want. And here I have a similar expression. So let me write it in this way. Sorry if I cancel. This will be the integral up to infinity. This is only up to time t. I have this contribution. And then I have us squared. And then I have ds. And then there is a martingale. And this is linear, so this is exactly, so you can write this as the integral, so integral to infinity, integral in lambda, and then you have indicator that s is less than big T, and then you have j. I can use the integral to put this, bring this operator here, it's self-adjoint. So I have this, and then I have us, so this is plus 1/2 us time us. Okay, you have something like this. Yeah, okay, you want to complete this square, okay? So this is very difficult to do at the blackboard because I always get it wrong, but let's try to do it. Complete the square. Yeah, so this is quadratic, this is linear in u, so essentially you want to write u plus half of this. Sorry, I have 1/2 actually. I take 1/2 outside, so I already have the 2. So this is 1/2, the integral in time, the integral in the space variable, and then I have us plus what I have there. Squared, okay, so this give me u squared, give me this time u, which is twice there because I put 1/2 in front. And then give me a new term, and then give me the martingale. So this will be this minus, and now you have to subtract what I added, which is this term is essentially up to t so only, and then here it's up to infinity. JS W3 square S. Yeah, and then there is the martingale part, which I don't care because it will disappear as soon as I take expectation. Question? Okay, this part I don't care. It's there, it's non-zero, so if I take the average it's non-zero, but I don't care because I have a constant, a delta t, I had delta t, remember, okay, my expression was like, my original expression was wt, zt, power 4, minus, then I introduced this gamma t, mysterious for the moment. I'm not using, I will use it later, but I have also delta t. Okay, so I can choose this constant because the energy, so what is the bottom of the potential, I don't care, okay? I can move the potential wherever I want because it's, because you have still to normalize. So these potentials are defined up to a constant. This was used in just an no lecture because it does not put the z in below because you can choose the constant so that the integral of exponential of u is normalized. So I can choose this constant, so this can be absorbed by delta, okay, killed by delta. Okay, you choose delta t or you choose a part of delta t because we will have to kill other terms to be exactly the expectation of this term, okay? And then you're done. This is killed by the expectation, so you have this now. And you say, what I gained? Well, this disappeared, so certainly I'm start to progress because I don't see anything anymore at the large scale. I need to send t to infinity. So now the only thing I see is W3 at some scale with u. Okay, still this object is growing, so it's not good either because this will grow logarithmically with the scale. I have to integrate to infinity. This integral is not converging anyway. This provide a bit of decay, but just, yeah, let me observe this. So just you have a feeling, otherwise you will lose, I will lose you. later. This is really like now in Italian you say, well, okay, I don't. So JS, what is JS? Remember, JS was this operator, which is what remains sigma SD. Okay, so sigma S D concentrate D around S. Okay, so you have to imagine that D is of order S, and recall that D is essentially the square root of the Laplacian, okay, because this is the Fourier variable. So essentially JS now is of size. This concentrate things around S, so the Laplacian is of order S squared, and then you take minus 1. Okay, so this is of order S minus 1. You have to imagine like this. It's getting small, okay? It's getting small, so you are improving a bit the situation here, okay? But somehow this is the main difficulty, and now the idea is that you choose U to kill this term, okay? So of course you cannot fix U because U is a variational parameter, but we will say that U is minus this object. We do a change of variable because I don't want to deal with this term, okay? Not there. Plus another object. This is an intermediate step, so let me just, I call it W in the notes, is equation 50 in the notes, okay? When it appears, WS, okay? So you see my hero has been diminished a bit by the equation 50. So this is a change of variable, okay? So this is the definition of W. W is this difference, and now you have just, here it's WS, okay? This is just a change of, you are, Justin, you are not happy about that? Now, what's going on?
Well, it seems like you're just hiding the difficulty in the notation.
Okay, yeah, I could, yeah and no. The point is that this is, okay, you see, you should complain. I mean, you had the same doubt. Of course, because when you do it by hand, you seem very smart, and then at the end of the day you think. But actually, this not improve the situation. Why? Because actually, what's going on here? So why this object is so difficult that actually the measure in the limit will not be absolutely continuous to the Gaussian free field. Okay, this is the main difficulty, and this is what we want to get out of the method. Have a way to handle a measure which is becoming not absolutely continuous. So remember that U is the entropy of the shifted measure with respect to the base measure. So this entropy will be useless in the limit, so you don't want it. And that entropy was this object, okay? So U will not be in L2 in the limit. It will not be in L2 because it will look like this object plus something which will be in L2, okay? So this is the transition from something which is absolutely continuous to something which is not, but it's still a shift. So it's a good shift, but it's so irregular that the law is not absolutely continuous anymore. So essentially here, the problem is saying that the minimizer is a shift of the Gaussian free field outside the Cameron-Martin direction. And you see that U is the minimizer. Remember what is U and Z. So now Z, if you want to compute ZT will be something like the integral up to t of minus, well, up to minimum of Js W, sorry, this is 3, yeah? ds plus, and then you have the integral, well, you have J, and then you have the integral of Js W s ds. Okay, so now you have a new shift. So this is the novelty here, is that you have to be more precise to describe your variational class. Your variational class in the limit will not be all the L2 process, actually will be processes which are not in L2, but it will be something not in L2 plus something in L2. And then the residual entropy is this, okay? So you have just to change the point of view, and this will work. So because now this object will disappear from the variational problem. Yeah.
Kind of putting a control structure, not like a control of path.
Yeah, for the moment it's just the Prato de Bush. This is the Prato de Bush. I'm just shifting with a random function my process. Okay, you see, So the interacting field will be Gaussian free field plus this plus something else, okay? Yeah, you are shifting the control. Well, you are trying to get an approximate solution. You see, there will be the now, from the point of view of minimizer, you will have a minimizer which solves an equation, and then you try to describe the most irregular part of those minimizers. Okay, so this is the most irregular part of the control. The control become, so you're making your control problem more robust because you're fixing a bit. A priori is a change of variable. For finite t is a change of variable, okay? Because you can take this to be this plus something, okay? So I didn't do anything, but in the limit, this will rigidify, and I cannot go back anymore. So before the limit is the same. Okay, so this is the first, this is the easy trick, okay? But okay, it's a trick. I mean, I just did a change of variable, I did a shift. This is a deterministic quantity. I don't have to do anything. But now my variational problem looks like this. So now optimize W. Okay, so now I think is equivalent, but psychologically it's useful to think that I'm doing a change of variable, and essentially the minimization problem on U is the minimization problem of a new control diffusion where you have an additional drift, okay? Minimize W. So imagine, so now the interacting field will be the Gaussian free field plus this object, which I give it a name. Okay, this object, I call it is W3, okay, like that, because there will be a lot of objects. So I think, okay, so I give it a name like that. This object is that integral. And you check that that integral give a well-defined limit in distribution. So this object will exist in the limit. Okay, and then there is something else. There is the integral of W. Okay, so this is still, I'm controlling a part of this solution, but W3, this 3 strange infinity exists and belong to 1/2 minus kappa. Okay, so this is, you see, I improve. So it's not true that the problem moved. Otherwise, the proof will go away because this 1 over s already provide, you see, J is 1 over s. So this integral is almost convergent. So this diverge a little bit. Okay, essentially, let's look at this. Yeah, okay, I don't want to spend too much time on this because this is something one can check. Essentially, this object diverge in this way, okay? This will not converge, okay, because let's say if I control, yeah, where this 1/2 come is this kind of computation, okay? The size, let's say the size in L infinity of this will go like s to the power 3 over 2, okay, diverge, okay, let's say in L infinity, okay, if I want to estimate the size of this object. But you see the pieces, J, add a piece only at certain scale, so this is really a scale decomposition. So if you want to estimate the size of this object as a certain scale, okay, so if you want to estimate this will be more or less the piece of the integral around that scale, okay? You want the piece of the integral where s, remember, this localized around the scale 2i, and essentially you pick up the piece of the integral at that scale. So J will have size 2 to the minus I, and this piece will have this size, okay? So you will have 2 to the 3 over 2i, okay? So you get 1/2. Okay, so this gives you this behavior. Okay, so somehow this is the computation, and then you have to make. But this is like an orthogonal sum. It's very easy, okay, because every piece only every part of this integral influences a given scale. So if you only use triangular inequality, you have lost. But if you use the projector before, this projector essentially cut an infinite integral will bring in only a part of this finite part, and then you are done. Okay, then you can estimate. So this estimate is more or less trivial. Well, if you know this already, okay, if you know this estimate.
Just to be sure, in your definition of WS, you want to include the JS or not? Because you wrote two different...
The definition of this?
No, of the small WS in, you put the JS, but the line above, there
No, it's because this is u. Sorry, because I made a mistake. Here there is j square, okay? Because remember, this is u. The definition of z is essentially the integral of j of u, and then there is another j. So sorry, this brings you. So there is this j, then there is the j coming from the definition of z. So when you go from here to here, you have to integrate jus. So this is the definition of z. It's the shift, but then you have to color the shift. So z is related with u in this form, so you have j square, and here you have 1j. So this improves things, okay? This is an operator which increases the regularity of 1, essentially, okay? Because it's the inverse of the square of the Laplace. So you get this estimate. So you see the interacting field, so I don't have time, so I will continue this afternoon, I don't know when. The interacting field is the Gaussian free field. So the moral is the Gaussian free field plus something which is in C1 half. So this would not be in the Cameron-Martin of the Gaussian free field, which is H1, let's say. And then plus something in which this is in L2, so this object increased the regularity, so this will be in H1. Okay, so you see, we are getting a more detailed description, and we will have to do another step, which involve this term tomorrow, because also this term creates problems, because now, you see, I told you about, now what is Z? This is Z. So I told you about that we were safe, but we are not safe anymore, because this created a problem that Z is essentially, it has a part in C1 half and then a part in H1. Okay, so it will not be any more regular enough to be multiplied by this, which is in C minus 1. Okay, so this product will not be good, and even this product create problem. Okay, so I will have to expand again. I will have to use this trick, but with this more difficult object, which is quadratic in Z, I will have to do some operation, and I need some paracontrol calculus. So Saturday morning, instead of going at the beach, we will do some paracontrolled expansion. Okay, but let me stop here for now. Justin, you have a question? No, but Justin is unfair. There should be one question. Ali. You make me happy. Then I will. Yeah.
Could you simply explain this square, why we get the square on the fraction?
This square?
Yeah, no, the first.
No, I just do it. No, I mean, this quantity here, let's do this quantity. So this object is the square of u. Then you have the cross term, which is this one, because z dot s is ju of s. Okay? And j can be integrated, it's self-adjoint, so I bring it on the other side. So this object times that is exactly that object. And then I have this object square, but I remove. Okay? This is just completing the square. It's algebra. And then I say this object does not depend on the control anymore, so I can remove by choosing delta. And then I can remove this very unpleasant term by shifting u, okay? And I use a new variable. So now in the entropy, so let me maybe write this. Then we go to lunch. In the entropy, here you have, now the entropy is a bit different, okay? Here you have the integral of w, not u anymore, okay? And then you have to, we will do another shift to eat a piece, a very bad piece here, and what remains is okay, okay? But this requires a bit more surgery of this expression. Okay, let's go to lunch. I mean, you can ask me.